Over several weeks, the moon appears to physically change shape. It shrinks from a bright, glowing disk down to a razor-thin crescent, before disappearing. In reality, nothing is disappearing. The moon is a solid, dusty rock. It doesn't grow or shrink, and it produces no light of its own. It only appears bright because it acts like a giant spherical mirror, bouncing the sun's rays back toward Earth. Because it is a sphere, the sun is always illuminating exactly half of the moon at any given moment. If the moon is a three-dimensional sphere orbiting around us, why is the pattern of craters on its surface identical every single night? We never see the far side. This occurs because of tidal locking. Tidal locking is a gravitational effect where a smaller body takes the exact same amount of time to spin once on its own axis as it takes to complete one full orbit around its parent planet. By synchronizing its rotation and its orbit, the moon keeps one specific face permanently pointed at Earth. Since the moon is always exactly half-lit, and we only ever look at one side of it, the shape-shifting we see from the ground is a result of geometry and human perspective. To map how this geometry works, we use a top-down schematic of the Earth-Moon system. Incoming sunlight is represented by yellow arrows on the right. The corner box shows what a person on Earth actually sees. The cycle begins with the new moon. The moon sets directly between the Earth and sun. From our perspective on the ground, the illuminated half faces entirely away from us, leaving the side facing Earth in deep shadow. As the moon moves along its path, our viewing angle shifts. We can now see a sliver of that illuminated half. This is the waxing crescent, visible in the western sky just after sunset. A few days later, the moon reaches a 90-degree angle relative to the sun. We look sideways at the boundary between day and night. We call this the first quarter phase, appearing as a perfect half-circle of light. As it continues counterclockwise, more of the day side comes into view. This bulging shape is the waxing gibbous. Waxing simply means the illuminated portion is growing larger from our perspective. Finally, the Earth sits directly between the moon and the sun. Our vantage point perfectly aligns with the illuminated hemisphere, showing a bright circular disk, the full moon. Throughout the first half of the orbit, the moon didn't change. We simply watched the illuminated side come into view as our vantage point shifted. For the second half of the orbit, the process reverses. As the moon travels back towards its starting point, the visible light wanes or shrinks. We see a waning divus, the third quarter, and a final morning crescent before returning to a new moon. If Earth sits directly between the sun and the moon during a full moon, why doesn't Earth's shadow block the sunlight every single month? This side view shows that the moon's orbit is not perfectly flat. It is tilted by about 5 degrees relative to Earth's orbit. Most months, the moon passes safely above or below Earth's shadow. A lunar eclipse only happens when the orbit intersects that plane during a full moon, forcing the moon directly into the shadow. A phase is a predictable shift in our viewing angle of the lit side, whereas an eclipse is a temporary physical blocking of that light. If you track the moon against the background stars, its physical journey around the Earth takes exactly 27.3 days. However, the visual cycle from new moon to new moon takes 29.5 days. This 29.5-day cycle is the synodic month, which is the time required for the moon to cycle through all visible phases from Earth. The discrepancy exists because while the moon circles the Earth rushes forward along its own orbit around the sun. By the time the moon completes its 360-degree lap, Earth has moved millions of miles. The moon has to travel for about 2 more days to catch up and recreate the exact same angle with the incoming sun rays. Cosmic timekeeping requires us to track these simultaneous movements across the solar system, rather than viewing the Earth as a stationary point. The 29.5-day synodic month provided early civilizations with their first functional lunisolar calendars, allowing them to track the passing seasons. These lunar cycles still dictate the timing of major cultural events. In India, Diwali is timed to the new moon of Kartika, while Holi aligns with the full moon of Falguna. This geometry exerts physical force. As the moon moves, its gravitational pull causes the water in our oceans to bulge. As the Earth rotates through that bulge of water, coastal areas experience the daily rhythm of high and low tides, controlled by the alignment of the Earth, Moon, and Sun. The lunar phases act as a massive geometric engine, driving human culture and the physical rhythms of the planet. Step outside tonight and take a close look at the exact shape of the moon. By noting which side is illuminated and the time of night, you can calculate where the Sun and the Earth are positioned in the 3D void of space around you. If you track it for a full 29.5 days, you can watch the entire geometric mechanism unfold. This orbital geometry turns the night sky into a perfectly readable map of our solar system.